Hello, my name is Gilad Cohen from Tel Aviv University. I will present our research work, Simple Post-Training Robustness using Test-Time Augmentations and Random Forest. This is a joint work with Professor Giryes. Here we outline the problem. It has been shown over the years that deep neural networks are highly vulnerable to adversarial attacks. What is an adversarial attack? These images include very small and imperceptible changes from the original image, so that humans still perceive the original class, but deep neural networks see something else entirely. In this example, the original class is panda. After adding to it adversarial noise, the image still looks like panda to us, but the deep neural network is convinced with very high confidence that the image contains a given. Thus, adversarial attacks pose a great security risk when using deep neural network in sensitive applications. We propose a simple and easy-to-use strategy to robustify any pre-trained deep neural network without modifying its weight. This is the flow chart of our model. First, test-time augmentations are generated and fed into the pre-trained deep neural network. Next, we collect the deep neural net's logit outputs. In the training phase, we fit a simple random forest classifier using the logits obtained from both natural and adversarial test-time augmentations. The random forest learns to be robust against adversarial images by training on the entire set of test-time augmentations logit distribution. This fitting is done only once, and it is very fast. In the inference phase, we generate n test-time augmentations for a single image. We then obtain the deep neural network logits for it, and pass the logits to the random forest classifier. The inference executes a single forward pass on all the n test-time augmentations at once, and thus it is very fast. The test-time augmentation generator introduces geometric, color, blur, and noise transforms. All the above transforms are randomized to generate n test-time augmentation samples per image. In the inference phase, we collect all the deep neural network's logic outputs for all the test-time augmentation images. When using only the test-time augmentations for making the prediction, the inferred label is a simple argmax of the logit summation. We can do better than summing the deep neural net's logits. The aforementioned test-time augmentations of both the natural and adversarial images are fed to the deep neural network, and their logits output are used to fit a simple random forest classifier. This random forest is trained to predict the correct label of any image, natural or adversarial. Here we show a comparison of accuracies in percentage for various classifiers on CIFAR10, CIFAR100, SBHN, and TinyImageNet, all trained on ResNet-50. We bold-faced the best results. Ensemble is presented just as a reference, as it has an unfair advantage. So why are we using a random forest here? Can other basic machine learning models predict the correct label? We examined classic models such as logistic regression and SVM, and found that for the majority of adversarial attacks, the random forest model surpasses the classic models. We tested whether our augmented random forest approach, or ARF in short, merely masks the deep neural net's gradients. For that, we devised two adaptive attacks that aim to fool the model by adding a noise that will maximize the impact on the entire test-time augmentation set. Our adaptive attacks, A-FGSM and A-PGD, are defined and explained in the paper. Moreover, we employed the backward pass differentiable approximation adversarial attack on our model. This attack was proposed by Attali et al. To test whether a defense merely masks gradients. We trained a substitute model instead of the random forest, so we can exploit the gradient of the deep neural network and the substitute model. Here we can see that our ARF protection can maintain robustness only when combined with an adversarially trained deep neural network. Non-adversarially trained models are greatly attenuated by the BPDA attack. This implies that our model merely does gradient masking. Although BPDA can greatly lower the accuracy on its adversarial samples, its added noise is perceptible, and thus this is not a successful adversarial attack to deploy in practice. For example, the red arrow shows that when BPDA is applied, the lizard background is modified a lot with image artifacts. Moreover, BPDA on ARF adds a large noise on all the digits shown in SVHN. Thank you for listening. For additional questions, you can contact me in this email address.